Alrighty, y'all. Today we're taking a look at question 9 for homework number 2. And for this one, we're trying to find the potential energy of this whole mess that they've given us. So I'm just going to start by drawing that mess. So we're going to have our proton here. Since it's the helium nucleus, it's given that it's 2 protons and 2 neutrons. The neutrons aren't going to have any effect on the electric potential energy because they don't have any charge. So they're neutrally charged, neutral to that. Then we're going to add in the second proton that's going to be moving in from infinity, and that's going to be separated by a distance given up here. It's 10 to the negative 15 meters. Again, we're keeping everything in meters to keep our consistent units. So then we're going to use our change in potential energy equation, and that's going to be from our reference point, which this point we said it's coming in from infinity. It's coming in from infinity, which is infinitely far away. That's from our reference point to where we end up. And the reason we're using our infinity as a reference point is because the potential energy is going to be 0 there. So if we have our final potential energy minus our initial, and our initial is 0, that's just going to leave us with that final potential energy, which is what we're solving for. So our equation for this is Q times the electric field dot dr, right? So our electric field, as caused by this proton, is going to be that away, and our radius from that proton is like that as well, or like that when it's like infinitely far away. So since they're going in the same direction, the angle between our electric field and our dr, that's going to be, the angle between them is going to be 0, and the cosine of 0 is 1. So we're just going to be multiplying by 1, so that means we just get to multiply the magnitudes of those two vectors together. That means it's just going to simplify to, and it's also the negative integral. Almost forgot that. Integral from infinity to 10 to the negative 15th of Q, E, dr, right? And since this is just a point charge, we're going to be looking at the field caused by this proton here. So it's a point charge, so that can be our field, is just going to be our equation for our, just the equation for the field, Q over R squared, KEQ over R squared. And it's important to note, this Q here is the charge of this proton, which I'm going to call 1 and 2. It's going to be Q1. And the Q over here is the charge of this proton. So, well, the charges are the same, but if they weren't, we'd have to keep this straight. But that's Q2 there. So that we can plug in to our equation down here. That's going to give us negative integral from infinity to 10 to the negative 15th of Q2 KEQ1 over R squared dr. And what a funny coincidence, but if we take this charge here, move it up here, get that dr out of the way, we just have Coulomb's law, which makes sense because our potential energy can also be written, it's the opposite of the work, and the work is the force times the dot product between the force and the dr as well. So it makes sense. It's great. So now just to make this integral simpler, I'm going to pull out these constants up here because obviously K is a constant and our charges aren't changing. So that's going to give us negative KE Q1 Q2 times the integral from infinity to 10 to the negative 15th of R to the negative 2 dr. Then we can use our power rule on this integral over here to get that it's just going to evaluate 2 r to the negative r to the negative 1. That's evaluated between infinity and 10 to the negative 15th. So if we plug that back in, we get our, and I'm just going to multiply this negative with this negative. So that's just going to get rid of the negatives in their entirety. So we're going to get KE Q1 Q2 over, well, I'll just keep it separate for now. It's going to be 1 over R evaluated from R equals infinity to 10 to the negative 15th. And you can't technically plug in infinity because it's not a number, but I'm just going to use a limit to evaluate that. So when we plug in our bounds, that's going to be KE Q1 Q2 times 1 over 10 to the negative 15th minus the limit, as just use x, any random number, doesn't matter, or any random letter, any random variable, as that approaches infinity of 1 over x. We remember from calculus that as this number is going to get, as the denominator gets really, really big, or as it's approaching infinity, this entire value is just going to go to 0, so you can just get rid of that. And we are left with, finally, KE Q1 Q2 all over r squared. Oh, sorry, not r squared. Ignore that. It's not over r squared, because that would be Coulomb's law again. This is just over 10 to the negative 15th. That is our equation. So now we're going to start plugging in charges and all that jazz. So it's going to be KE times the charge of the first proton, which is 1.602 times 10 to the negative 19th. Again, I'm keeping it in coulombs. And I'm lazy, so that in the charge of the second electron is the same exact magnitude, and it's also positive. So I'm just going to square it, because it's just multiplied by itself, and then divided by 10 to the negative 15th. If you plug all this into your calculator, obviously using our KE equals, ooh, I'm talking fast, 8.99 times 10 to the 9th. Plug all that into your calculator, that's going to get you your answer for the potential energy, but since we kept all of our units constant and everything, it's going to give you your answer in joules. Now, I don't have the screenshot of it up right now, but all of the units for the Kudu answers are either in electron volts or like mega electron volts. I don't know if it's actually mega, but I'm going to call it mega because, I don't know, because I am. So we have our answer in joules, but we have to get into electron volts. So let's take another quick look at our equation over here, right? So if we can rewrite this, 1.602 times 10 to the negative 19th, that's just the magnitude of the charge of an electron. It's going to be KE times E times E, or E squared, but I'm just going to write it all out. That's all over 10 to the negative 15th, right? So we have that now, right? If we take this E and move it over here, suddenly we have we're dividing out this charge just real quick. We have U divided by charge. That's going to give us our electric potential instead of our electric potential energy, right? So what we have now is this is in volts. This is in volts. That's an electron. So that is going to give us, if we have KE times 1.602 times 10 to the negative 19th over 10 to the negative 15th E, but this is in volts. That's going to get you your electron volts, right? And spoiler alert, we can look right now, this is to the negative 19th, this is to the negative 15th. You're going to get something that's, it is just, take my word on this for right now, you're going to get some answer that's times 10 to the 6th, right? It's going to be times 10 to the 6 electron volts, and that's going to give you your mega electron volts, because 1 times 10 to the 6 electron volts, that's your mega electron volts, one of those. Or 1 electron volt is 10 to the negative 6 mega electron volts. Either way, just check your answer that it's in the right units, and you'll be good to go. All right, well, thank you so very much for watching. Let me know if you have any more questions about this problem or any other problems that you'd want me to try to walk through or explain, and I'll do my best to explain them, because I guess Sydney explains stuff.